Hello student, I am Dr.A.K, Professor of Chemistry. Today I am going to discuss physical and chemical properties of P block elements. The atomic physical and chemical properties of 13 elements I am going to discuss. Okay, properties of atomic physical and chemical properties of group 13 elements. Okay, electronic configuration. First I will discuss electronic configuration. The outer electronic configuration of group 13 elements is ns square np1 in general way. Okay, a close look at the electronic configuration suggests that while boron and aluminum have noble gas core, gallium and indium have noble gas plus 10d electron, and thallium has noble gas plus 14 electrons plus 10d electrons cores. This is a very important regarding electronic configuration. Again you listen. The outer electronic configuration of group 13 elements or boron family is ns square np1. First important things. And close look at the electronic configuration suggests that while boron and aluminum, only these two, boron and aluminum have noble gas core. Okay, now you can see difference. Aluminum, I told you, boron and aluminum have noble gas core. Gallium and indium have noble gas plus 10d electrons. This is about gallium and indium. Now third difference you can see, thallium has noble gas plus 14f electrons plus 10d electrons. See how they are differing. Aluminum, this boron and aluminum was not having D and F, only noble gas core. But after that, gallium and indium, they have noble gas core plus 10d electrons, and thallium have noble gas plus 10d electrons plus 14f. Means you can tell that thallium have 14f electrons plus d electrons. Okay, plus that core, noble gas core. Now I told about the electronic configuration. This is very important. P block, all elements, almost all elements down, their properties are different due to that. Thus the electronic structure of these elements are more complex than for the first two groups of elements. Okay, means first and second group, it is different. The difference in electronic structure affect the other properties and consequently the chemistry of all elements of this group. Okay, now one by one I am telling you. First, atomic radii. On moving down the group, for each successive members one extra cell of electrons is added. On moving down the group, for each successive member, one extra cell of electrons is added, and therefore means one new orbit will be opened as you will go down. Therefore, atomic radius is expected to increase. However, its deviation can be seen. Atomic radius of gallium is less than that of aluminum. It should be more, but gallium it is found less. Atomic radius of gallium is less than that of aluminum. Why? This can be understood from the variation in inner core of electronic configuration. Okay. The presence of additional 10d electrons offer only poor screening effect for the outer electron from the increased nuclear charge in gallium. Means in gallium positive charge increased, but electrons are not shielding properly to the outermost. Okay, due to that it is becoming less. It should be more, but it is less because nuclear charge becoming more, positive charge, and outside electrons, outermost electrons have effect on nucleus, and they are coming back. Okay, it is attracting because inside between the nucleus and outermost orbit, many d electrons are there. Then they are not shielding properly. That's why. Okay, it is becoming small. Okay, atomic radius decreases. This I have told you. Now I told about the gallium. Consequently, the atomic radius of gallium, that is 135 picometer, is less than that of aluminum. Aluminum radius is 143 picometer. Atomic radius for aluminum is 143 picometer. Gallium 135 picometer less. Now next property, that is the ionization enthalpy. The ionization enthalpy values are expected from the general trends do not decrease smoothly down the group. Okay, this should actually decrease, but it is not decreasing down the group. The decrease from boron to aluminum is associated with increase in size. The observed discontinuity in the ionization enthalpy values between aluminum and gallium and between indium and thallium due to inability of d and f electrons, which have low screening effect, to compensate the increase in nuclear charge. Nuclear charge, for every electron it is increasing, one proton will increase. For each electron, one proton will come. But what is happening in that, charge is increased, but in comparison to the charge, they are not shielding properly. Outermost electrons. Hence they have attraction. Outermost electrons are going to be attracted and size will become small. This is the main reason. Okay. The order of ionization enthalpy as expected is delta H. The order of ionization enthalpy is as expected as delta H. First, there are three ionization energy. First ionization energy, second ionization energy, third ionization energy. When one electron will be removed, then first ionization energy, second if it will be removed, then how much energy is involved? That is the second ionization energy. And third, how much energy is required to remove? That is the third ionization energy. Okay. Then here this is first ionization energy. First ionization energy is less than second, and second is less than third. Okay. Then now reasoning you are understanding why first is less, because first in comparison to first ionization is second and third, then second and third are nearer to the nucleus, hence it is difficult to remove. First one is comparatively far, hence it is easy to remove, hence less energy, ionization energy in the case of first ionization is less, second is more, and third is further more. Okay. The sum of the first three ionization enthalpies for each of the element is very high. Okay. Average you are taking, the sum of the first three ionization enthalpies for each of the element is very high, and this you will see that how it is affecting. Okay. Now next property is electronegativity. Then you know in general that p block elements are electronegative, means they want electron, they can attract the electron in a molecule. Down the group, electronegativity first decreases from boron to aluminum and then increases. Okay, first it will decrease from boron to aluminum and then it will increase marginally. Okay, this is because of the discrepancies in atomic size of the elements. Okay, because they are not in a proper way, whereas D and F is there, D electrons are there, F electrons are there, then the discrepancies are there. That's why it varies. Okay. Now I am talking about the physical properties. Okay. Boron is non-metallic in nature. Boron is non-metallic in nature. It is extremely hard and black colored solid. It is a black colored solid and very hard. It exists in many allotropic forms. Boron, it exists in many allotropic forms due to very strong crystalline lattice. Okay. Due to very strong crystalline lattice, boron has unusually high melting point, very high melting point. It is hard also, and this is due to this strong crystalline lattice energy. Rest of the members are soft metals. Okay, boron is hard. Rest of members are soft metals with low melting point and high electrical conductivity. Melting point and high electrical conductivity. Okay, this boron I told you it is hard. Boron is hard. Rest of the this hard and black in color, black color solid. But other elements, then rest of the members are soft metals with low melting point and high electrical conductivity. It is worthwhile to note that gallium with unusually low melting point, its melting point is low, 303 Kelvin only, means 30 degrees centigrade. 30 degrees centigrade. Here for gallium, you should know that melting point is low. Okay, with low melting point and high electrical conductivity. And very, very important is that it is about the gallium I am talking about. It is worthwhile to note that gallium with unusually low melting point, it will melt very quickly, means only 30 degree with unusually low melting point could exist in liquid state during summer. Actually, mercury, you know that mercury is a liquid metal. Hg is a liquid metal. Okay, at room temperature mercury is liquid, but gallium is also liquid. The question is asked, but only thing is that is near about 30 degree. In summer it will melt. In summer 30 degree is common, but mercury will be always 25 degree also. At room temperature 25-27 degree it will be liquid, but gallium also is liquid. 30 degree is the melting point, 30 degree centigrade, that is 303 Kelvin. This is the important thing. It's a high boiling point. Boiling point is very high. That is the 2676 Kelvin, 2676 Kelvin makes it. Then, but this boiling point, high boiling point, is making it useful. Its high boiling point makes it a useful material for measuring high temperature. Okay. Density of elements increases down the group from boron to thallium. Gallium I am talking about, its role is that because of high boiling point 2676, it is a useful material for measuring the high temperature. Okay. Now I am telling some important atomic and physical properties of group 13 elements, means boron family. Atomic number, you know that boron is the first member, second is the aluminum, third is gallium. Boron is B, aluminum is Al, gallium is Ga, indium is In, In means indium, and Tl means thallium. Then atomic number is for boron 5, aluminum 13, gallium 31, indium 49, and thallium 81. And atomic mass, just I told in the beginning, up to atomic number 20 it will be roughly double, and after that it will vary. Then now boron is 5, then atomic mass is 10.81, roughly double. And aluminum is 13, then his atomic mass is 26.098. And gallium is 31, then see it is more than double, 69.72. And indium is 49, then it is atomic mass is 114.82. And thallium Tl 81 is the atomic number, and 204.38, that is the mass number, atomic mass. Now come to the electronic configuration. Already I have discussed. Boron is 5, then helium electronic configuration, and extra is 2s2 2p1. And aluminum neon configuration, and extra is 3s2 3p1. And argon, this things, gallium argon configuration, and after that 3d10 4s2 4p1. See, before p2 are there, 3d10 4s2 4p1, that is for gallium Ga. And for indium In, then krypton electronic configuration, krypton, after that 4d10 5s2 5p1. And this thallium metal 1, then electronic configuration of GNN, Xe, GNN, after that 4F14, F is also there, 4F14, 5D10, 6 square, 6S square, 6P1, okay, 6P1. Then this I have told about the boron, aluminum, gallium, indium, thallium, also called boron family, group 13. Now just you see atomic radius. Then in picometer it is 88 for boron, 88, aluminum 143, it is bigger, and gallium 62, decreased from decreased 135. Aluminum is 143 picometer atomic radius, and gallium 135, decreased. After that indium 167, that is increased. Thallium 170, increased. Means here 88 for boron, gallium 135, indium 167, thallium 170. Means all are increasing except this aluminum, gallium is 135. After that all are increasing. Boron 88, after that aluminum 143 increased, indium 167, thallium 170, all are increasing. Exception is gallium, it is decreasing. Keep in mind. That's why it is showing different type of property. Ionic radii you can see M3 plus means when all 3 electron will go outside, then M3 plus it will form. Then what is radius? Picometer. Then for boron it is a 27 picometer. Aluminum is 53.5, and gallium 62, indium 80, and thallium 88.5. all are increasing, but boron is 27. Till date it is not 100% confirmed, but 27 you can consider. 27 boron, aluminum is 53.5 more, gallium 62 again more, indium is 80 again more, thallium is 88.5 again more. Okay. Ionic radius I have told you. Now I am going to tell ionization enthalpy. Ionization enthalpy kilojoule per mole. Then there are three ionization energy, H1, H2, H3. Then you see the boron. In the case of a boron, all 3. For the first electron, there are outermost 2s2, 2p1, 3 electrons are there. Then how much energy will be required to remove the electron? Then 1 by first electron, if you will remove, then 801 you can say kilojoule per mole energy is required, 801. Second, more 2427, second ionization energy. And third, again further more, 3659 kilojoule per mole. That is for boron, I told you. Like that way, aluminum is less. 577, 1816, 2744. This is for ammonium, less, this is less than boron. Now for gallium it is more, little more, 529, 1979, 2962. It is more than aluminum. Okay, and next indium. Indium is further less. It is less actually, less than gallium. That is 558, 1820 and 2704. This is less than gallium. Now last you can see that is the thallium. Thallium is more, 589, 1971, 2877. Here trend is telling that boron has more energy. Sum, if you will make all three, you will make a sum, then it is more. It is more than aluminum. Aluminum is only you can say less. Or if you will count from this, boron is more. After that, it is decreasing. It is not decreasing. Boron is highest, and after that, aluminum is less, and gallium is little more, and again indium is little less than aluminum and less than gallium, and thallium is again more than these three. More than these three means aluminum, gallium, indium, thallium is more. Okay. Now come to the electronegativity. Then boron has 2.0, means it will not react too much. Boron, because plus 2.0 means it is unreactive like that. And aluminum is again 1.5, plus 1.5. It is also not very reactive. Okay, but it is more reactive than aluminum is more reactive than boron. Now come to the gallium, 1.6. It is again not very reactive like aluminum. Indium is also 1.7, not very reactive, and thallium is 1.8. Plus sign means very less reactive. Then boron 2.0, aluminum 1.5, gallium 1.6, indium 1.7, thallium 1.8. Means comparatively in all these elements, 5 elements, aluminum is more reactive. Okay, more reactive, because its value is less, plus 1.5. Density means heavier. You can see density, gram per cc at 298 Kelvin. 298 Kelvin means 25 degrees centigrade. Then density of boron is 2.35, and for aluminum 2.7, and gallium is very heavy, 5.9, and indium is further heavy, 7.31, and thallium is again very heavy, 11.85. Okay, melting point of boron is very high, 2453, and for aluminum 933 only, 933, and gallium, I told you 303 melting point. Melting point means 30 degrees centigrade. It is liquid at 30 degree. In summer it is liquid. Indium its melting point is 430, and thallium 576. Okay, here gallium you have to keep in mind, it is a very less melting point, only 30 degree, means 393 Kelvin. Boiling point is too much for all. That boron is 3923, very high boiling point. Okay, aluminum is less, 2740, but here boron is 3923, around 4000. See, 3923, and aluminum is 2740, and gallium is 2676, indium is 2353, and thallium is 1730 less. And now come to the this electrode potential, reduction potential. I am telling you, this electronegativity, I just electronegativity, again you listen, that electronegativity of boron is 2. Boron electronegativity is 2, and for aluminum it is 1.5, gallium is 1.6, indium is 1.7, and thallium is 1.8. Means it is telling that boron wants electron more than others. Boron bonds electron more than other elements. Now I am talking about the reduction potential. That shows about the you can say how much which elements have you can say natural tendency to lose the electron. That is the basic property. Okay, basic property. That is the potential, redox potential. Then this reduction potential, boron will, which is not data is not available, not it is forming only covalent bond. Now aluminum is a minus 1.66. Minus 1.66 means it is a reactive. Okay, and gallium is a less reactive, only minus 0.56, and indium is again further less reactive, minus 0.34. Thallium is further not reactive, it is not reactive, you can tell, plus 1.26. Okay, and this I have told that 3 plus, if they will lose all 3 electrons, that M3 plus is converting to M. M3 plus converting to M means M3 is there if they will get all 3 electrons. This is a reduction potential. Reduction means gain of electron. Then that time this value I have told you. Now if it is a 1 plus, in that situation they will all have particularly this aluminum will not react, plus 0.55, less reactive, if only 1 electron is M plus case, and minus 0.79, that is in case in the presence of acid it will react with gallium, and it will also react with in presence of alkali, that is more reactive than in alkali medium, minus 1.39, and indium is also reactive, minus 1.8, minus 0.18, and thallium is minus 0.34, means in plus 1 state all will be reactive and they can lose the electron also. Okay. Then this I have told you about the atomic and physical properties of group 13 elements. Now further I am going to tell these things. Chemical properties oxidation state and trends in chemical properties or chemical reactivity. Due to a small size of boron, the sum of its first three ionization enthalpy is very high. This prevents it to form +3 ions and forces it to form only covalent compounds. It will form only covalent compounds. Okay, because boron, because this is enthalpies are first three ionization enthalpy is sum of the first three ionization enthalpy is very high. Okay, only covalent compound it forms. But as we move from boron to aluminum, the sum of the first three ionization enthalpies of aluminum considerably decreases and is therefore able to form aluminum 3+. I told you the sum of the first three ionization enthalpies of aluminum. I am talking about the aluminum. The sum of the first three ionization enthalpies of aluminum considerably decreases and is therefore able to form aluminum 3+. 3+ it can form. You can lose 3 electrons. It can form 3+ ions. In fact, aluminum is a highly electropositively metal. However, down the group, due to poor shielding effect of intervening D and F orbitals, the increased effective nuclear charge holds NS electrons tightly, responsible for inert pair effect. What is the inert pair effect? I have already told you, again I am telling you that due to poor shielding effect of intervening D and F orbitals, the increased effective nuclear charge holds NS electron tightly. And when it is holding tightly, then what will happen? When it holds NS electron tightly, then responsible for inner pair effect. That 2 electron NS it will not lose. That will be, these 2 electrons will be inert. It is called inert pair effect, and thereby restricting their participation in bonding. As a result of this, only a p orbital electrons may be involved in bonding. Okay. In fact, in gallium, indium and thallium, both +1 and +3 oxidation states are observed. The relative stability of +1 oxidation state progressively increases for heavier elements. +1 oxidation state progressively increases. +1 oxidation state for heavier elements means aluminum is less than gallium, gallium is less than indium, and indium is less than thallium. Okay, in thallium +1 oxidation state is predominant, means thallium will found always in +1 oxidation state. In thallium, +1 oxidation state is predominant, whereas the +3 oxidation state is highly oxidizing in character. +3 oxidation state is highly oxidizing in character. The compounds in +1 oxidation state is expected from energy consideration are more ionic. Here, the compounds in +1 oxidation state, as expected from energy consideration, are more ionic than those in +3 oxidation state. Okay, +1 oxidation state is more ionic because it can lose the electron, but +3 means it is difficult to lose the electron. That's why +1 is more ionic. In trivalent state, the number of electrons around the central atom in a molecule of the compounds of these elements, particularly boron in BF3, will be only 6. Already know that boron is electron deficient compound. Boron in BF3 will be only 6 such that is electron deficient. Such electron deficient molecules have tendency to accept a pair of electrons to achieve a stable electronic configuration and thus behave as a Lewis acid. Any species which accept a pair of electrons, that is called Lewis acid. It behave as a Lewis acid because it requires a pair of electrons to achieve a stable electronic configuration and thus behave as a Lewis acid. The tendency to behave as a Lewis acid decreases with increase in the size down the group. BeCl3 easily accepts a lone pair of electrons. Barium trichloride, boron trichloride, BeCl3 easily accepts a lone pair of electrons from ammonia to form BeCl3 NH3 compound. Because ammonia has lone pair of electron. Ammonia has a lone pair of electron NH3. Then that electron can be given to BeCl3. Boron is electron deficient, hence it will take. Then NH3 will form coordinate bond with boron trichloride, BeCl3. It will form tetrahedral compound, BeCl3 NH3. BeCl3 NH3. This is a tetrahedral. And aluminum chloride, AlCl3, achieves stability by forming a dimer. AlCl3 is also these things. They lack electron deficient. AlCl3 is also electron deficient molecule, but it will get a stability. It achieves stability by forming a dimer. It will repeat. AlCl3, 2 AlCl3 will come and it will form Al2Cl6. Okay, and it is called dimer. Then AlCl3, again AlCl3. Then this AlCl3, they will join to each other. Al will attract Cl. Al is electropositive, Cl is electronegative. Hence both will attract. Correct? And in this way they will form dimer. Aluminum and chloride both will attract to each other because one is electronegative, other is electropositive. Hence that AlCl3, they will dimerize. In trivalent state, most of the compounds being covalent are hydrolyzed in water. Again, this is important. In trivalent state, most of the compounds being covalent are hydrolyzed in water. For example, trichlorides on hydrolysis in water means H2O that will break in H and OH. For example, the trichlorides ion hydrolyzes in water and form tetrahedral MOH4 1-. Okay, tetrahedral MOH4 it will form. M means metal. It will form tetrahedral species. The hybridization state of element hybridization state of element M is sp3. sp3 means total 4 valency. S and p3, 3 are there now, sp3, sp3, sp3. Then it will have total 4 valency. Okay. The hybridization state of element M is sp3. Total 4 valency will be there. Aluminum chlorides in acidified aqueous solution. Aluminum chloride in acidified aqueous solution forms octahedral, means AlH2O whole 6 3 plus complex it will form. Okay. Aluminum chloride in acidified aqueous solution forms octahedral ion. Octahedral ion means AlH2O whole 6 3 plus. In this complex ion, the 3 d orbitals of aluminum are involved and the hybridization state of aluminum is sp3d. Here it is important. In this complex ion AlH2O whole 6 3 minus, here 3 d orbitals of aluminum are involved and hybridization state of aluminum is sp3d2. sp3d2. Okay. And they form this sp3d2 3 2 plus 1 6. Okay. This is the octahedral. And one question is asked that I am explaining. Question they will ask, standard electrode potential value E0 for aluminum 3 plus oblique aluminum is minus 1.66 volt, and that of thallium 3 plus converting to thallium is plus 1.26. Predict about formation of M3 plus ion in solution and compare the electropositive character of the two metals. Okay, this question is asked in examination. Again, question I am reading. A standard electrode potential value of E0 for aluminum ion. Aluminum 3 ion is converting to aluminum, means Al3 plus oblique Al reduction. Its value is minus 1.66 volt. That of thallium 3 plus, it is converting to thallium, means thallium 3 plus oblique thallium reduction. Its reduction potential is plus 1.26. Predict about the formation of M3 plus ion in solution and compare the electropositive character of two metals. Already I told you this type of question has easy explanation. Minus means very, very reactive and it has tendency to lose the electron. Correct? Then this aluminum when it converts to aluminum ion 3 plus convert to aluminum, it is a reduction potential is minus 1.66 volt. Minus, it is more reactive and more tendency to lose the electron. Thallium is Tl3 plus converting to thallium is plus 1.26, less reactive, less tendency to give the electron in solution. Then explanation, now understand. Standard electrode potential values for two half cell reaction suggest that aluminum has a high tendency to make aluminum 3 plus. It has more tendency to lose the electron in solution, in aqueous solution, whereas thallium 3 plus is not. Okay, it is not has tendency, so much tendency as aluminum. Only unstable, what will make, will not lose the electron but will become unstable in solution, but is but is a powerful oxidizing agent, because they are not able to natural tendencies to lose the electron, but have these things they are unstable in solution, hence it can give the electron. That's why they are powerful oxidizing agent also. Thus thallium is more stable in solution than thallium is more stable in solution. Thallium 1 plus I am talking about. Thallium 1 plus is more stable in solution than thallium 3 plus. Aluminium being able to form plus 3 ions easily is more electropositive than thallium. Okay, this question is asked. I explained. Now, reactivity we can see. Reactivity towards air. Boron is unreactive in crystalline form, unreactive. Aluminium forms a very thin oxide layer on the surface, which protects the metals from further attack. Amorphous boron in a powder form. Amphoteric is different. Amphoteric is acidic and basic character. Both will be there. It is amorphous. Amorphous means powdered form. Amorphous boron and aluminum metals on heating in air form B2O3 and Al2O3. Okay. Amorphous boron and aluminum metal on aluminum is a metal, metal on heating in air form B2O3 and Al2O3 respectively. With nitrogen, N2 gas, with N2 at high temperature they form nitride. Questions are important. These are asked. Then this I told you that it will form B2O3 boron, and in general 2E plus 3O2 you can tell. E means element. Then 2E, that is a solid, plus 3O2, it form 2E2O3 just like B2O3 or Al2O3. And again with nitrogen it will form aluminum nitride. 2E plus N2, 2E plus N2, 2EN means aluminum nitride. 2En means aluminum nitride. Okay. Then this I have told about the reactivity towards the air. The nature of these oxide varies down the group. Boron trioxide, again important question. Boron trioxide is acidic and reacts with basic oxides. Obviously, when boron trioxide is acidic, then it will react with basic and reacts with basic metallic oxide, forming metal borate. Metal borate, after the reaction it will form metal borate. NO2B4O7. Aluminium and gallium oxides are amphoteric. Amphoteric means acidic and basic nature. Both nature it have. It can function as acid or base. Aluminium and gallium oxides are amphoteric, and those of indium and thallium are basic. Question is asked. Aluminium and gallium, okay, these are amphoteric, means can behave as acid and base, and those of indium and thallium are basic in their properties. Don't forget. Now reactivity towards acid and alkalis. How they will react with acid and alkalis? Then boron does not react with acids and alkalis. Even at moderate temperature it will not react with acid and bases. But aluminum dissolves in mineral acid and aqueous alkalis and thus shows amphoteric behavior or character. Aluminum dissolves in mineral acid also and base also. Aluminum dissolves in mineral acids and aqueous alkalis and thus shows amphoteric character. Aluminum dissolves in dilute HCl and liberate hydrogen gas, means 2Al plus 6HCl. Balanced equation. 2Al, Al is solid, plus 6HCl, that is aqueous solution. It forms aluminum ion 2Al3 plus 6Cl minus chloride ion plus 3H2, means hydrogen gas. It gives 3 product. 2Al plus 6HCl, it gives 3 product. Aluminum ion 2Al3 plus chloride ion, means 6Cl minus plus 3H2O. 3H2 gas, hydrogen gas. Okay. However, concentrated nitric acid renders this nitric acid makes aluminum passive by forming a protective oxide layer on the surface. That's why it is called that nitric acid renders aluminum passive by forming protective oxide layer on the surface. Due to this layer, it will not react further. That is called renders nitric acid renders aluminum passive. Passive means it will inactive. Okay. Aluminum also react with aqueous alkali and liberates hydrogen gas. Very, very important reaction. Means 2Al plus 2NOH. 2Al plus 2NOH plus 6H2O. 3 reactants are there. 2 aluminum plus 2 NOH plus 6 H2O. It forms tetrahydroxyaluminate. Product is important. Tetrahydroxyaluminate third, means it forms 2 molecules of Na plus AlOH whole 4 minus, okay, Na plus AlOH whole 4 minus 2 molecules, okay, and 3H2 hydrogen gas. Main product is tetrahydroxyaluminate third. This is very, very important reaction. Again I am telling there this thing's formula. It gives 2 molecules of 2Na plus AlOH whole 4 1 minus. Now reactivity towards halogen. Reactivity towards halogen. These elements react with halogen to form trihalides, means TLI3. Okay. They form TLI thallium, means thallium iodide it will form. Then 2E, in general 2E, E means element, 2E metal is element is solid, 2E plus 3X2, 2EX3, where X is equal to fluorine, chlorine, bromine, iodine. Okay. Now here one more question is there which is asked in examination, just to understand. It is important question. While fumes appear around the bottles of anhydrous aluminum chloride, give reason. If you will see the bottle of aluminum hydroxide chloride, anhydrous aluminum chloride, anhydrous, no water molecules, anhydrous aluminum chloride AlCl3. If you will see the AlCl3 bottle, anhydrous, no water molecule. Then near the bottle, always you will find some fume. If you go to the laboratory, you will see aluminum chloride bottle. Near the aluminum chloride bottle, always fume will be there. Why this fume? This question is asked. Then now I am telling the answer. Answer is very easy and conceptual. Anhydrous means there is no water molecule, very clear. AlCl3 has no water molecule. But now you can see anhydrous aluminum chloride is partially hydrolyzed with atmospheric moisture. Where bottle is there, outside in atmosphere, moisture will be there. Then this AlCl3 will react with moisture, H2O, and it will form HCl gas, hydrogen chloride gas. Okay. Anhydrous aluminum chloride is partially hydrolyzed with atmospheric moisture to liberate HCl gas, and moist HCl gas appears white in color. Okay, white in color. That's why you will see the fumes. You will see you can say white fumes around the bottle of anhydrous aluminum chloride. Today I am stopping only here. Next class and we will meet. Thank you.